everyone, this is Dr. Seema Shah Fairbank, and in this video we will use Excel and show how to calculate normal depth based on the Manning's equation using GoalSeek.
As you may recall from earlier, we learned that uniform flow occurs when you have a constant flow in space and constant in time. The flow can be determined using the Manning's equation. When the friction slope SF is equal to the water surface slope SW, which is equal to the bed slope S0, we've got uniform flow. Phi is equal to 1 in metric units and 1.49 in English units. Q represents the flow rate, N represents the Manning's roughness, which can be looked up in a table. A represents the cross-sectional area, and R represents the hydraulic radius, which is the area divided by the wetted perimeter. And SF represents the friction slope. Note, depth determined under a uniform flow condition is called normal depth. Let's test out an example that we had done by hand. We calculated the normal depth for a channel that has a slope of 0.1%, a Manning's roughness of 0.03, and a flow rate of 250 CFS. The channel has the following geometry: 3-to-1 side slopes and a base width of 5, making it a trapezoidal channel. To solve this, we'll use the Manning's equation, where Q is equal to 1.49 divided by N times area times the hydraulic radius to the 2/3 power times the slope to the 1/2 power. We know that the area for a trapezoidal channel is equal to the base times the depth plus the side slope times the depth squared. And we know that the wetted perimeter is equal to the base plus 2 times the depth times the square root of 1 plus side slope squared. And the hydraulic radius R is equal to the area divided by the wetted perimeter. When we enter this into the equation, we have 250 CFS is equal to 1.49 divided by 0.03 times the quantity of 5 plus 3dn times dn, all raised to the 5/3 power, divided by the quantity 5 plus 2dn times the square root of 1 plus 3 squared, that entire quantity raised to the 2/3 power, times our slope of 0.001 to the 1/2 power. As you can tell in this equation, our dn is embedded within the equation, making it difficult to solve easily. As a result, we are going to use GoalSeek in Excel.
So now we're ready to enter this into Excel. We were given a flow rate of 250 CFS, a Manning's roughness of 0.03, a normal depth that is unknown. So I'm going to highlight this cell in yellow. And this is going to be what we're going to GoalSeek. Our base width is 5, our Z is 3, our slope is 0.001, and our area is a calculation. Our wetted perimeter is a calculation, and our hydraulic radius is a calculation. I'm going to highlight these in green and program them. Our flow rate needs to be 250. This is going to be associated with our GoalSeek, but it's also calculation. So we're going to put in our area. Our area for a trapezoidal channel is our base width times our depth plus our Z times our depth squared. Now you'll notice you're getting 0. So let's put a dummy variable in for normal depth of 1. It'll give us our area. Now let's calculate our wetted perimeter. Our wetted perimeter is our base width plus 2 times our depth times the quantity of 1 plus Z squared raised to the 1/2 power, or square rooted. Our hydraulic radius is our area divided by our wetted perimeter. Our flow rate is 1.49 divided by N times our area times our hydraulic radius raised to the 2/3 power times our slope raised to the 1/2 power. When we have a depth of 1, we're getting a flow rate of 10 CFS. If we have a depth of 10, we'll get 1600 CFS. If we have a depth of 5, we're getting 300 CFS. So what's helpful is, instead of trial and error or using the bisection rule, we can go under Data, What If, GoalSeek, where we want to set the flow rate in cell B10 to 250 CFS. And we want to change the normal depth, DN, in cell B3. And we hit OK, and we will get 5.68. Now, you can clean this up and just show the significant digits. So 4.6 feet is the normal depth. So why don't you try it on your own and comment in the video if it works for you.